We're moving on into our list of topics that are essential in order to be able to do the dosage calculations coming up in Unit 3. Also, some of these skills are essential for other classes you would have to take if you were going on into a medical related field. Today's topic is actually most important if you're going on to do the chemistry and anatomy and physiology courses that would be required in most programs. So just a quick review of something we've already done with our exponents. Things like x to the 8th times x to the 13th. We've already shown that when we multiply exponents with the same base, if you recall, every exponent has two parts. So here, x to the 8th, x is the base of the exponent, and 8 would be the power of the exponent. And so when we're combining, multiplying, or dividing exponents with the same base, in this case, both of these have a base of x, when we're multiplying, we would add the powers. So this is going to be x to the power of 8 plus 13, or x to the power of 21. And if we had variable or numbers with our variables, like 9 y to the 12th times 3 y to the 19th, we would treat it just like any other number. We would do the numbers first, counts first. 9 times 3 is 27. And then we would do the names. Y to the 12th times y to the 19th. They both have a base of y, so we keep the base of y. And we add the powers. 12 plus 19 is 31. We also had division. If I had x to the 18th divided by x to the 7th, we saw the same thing. These both have the base of x again. So our solution is going to be just an exponent with a base of x. And now when we divide, we subtract the powers. 18 minus 7 is going to give us x to the 11th. And if there's numbers in with the variables, like 32 y to the 15th divided by 4 y to the 7th, we divide the numbers, counts. 32 divided by 4 is 8. And then we deal with the exponents as the name. Y to the 15th divided by y to the 7th. Well, they both have a base of y. And then we subtract the powers. 15 minus 7 is 8. So we get 8y to the 8th. And then finally, we had x to the 5th, the power of 7. And here we have a power of a power. So the base doesn't matter. There's only one base here. That's the x. Then we have a power of another power. And so in that case, that was the base of x to the power of, we multiplied the two powers. So 5 times 7. That gave us x to the power of 35. And again, if there's a number in there, let's say we have 5 y to the 8th to the power of 4. We take the number, still has to go to that power. 5 to the power of 4 is 5 times 5 times 5 times 5, which is 625. And then y to the 8th, base of y, 8 y to the 8th to the power of 4. 8 times 4 gives us power of 32. This was also the basis for some of our negative powers. The definition of an exponent and powers, negative powers don't make a lot of sense. Like 10 to the power of negative 3. That's saying we're going to have negative 3 tens multiplied together. That really doesn't make sense. 10 to the 3rd makes sense because that is saying there are 3 tens multiplied together. 10 times 10 times 10, giving us 1,000. So to figure out what this 10 to the negative 3 meant, we used that pattern. Remember, we did this for multiplying two negatives, and we've done it for other things where the basic definition doesn't make sense. But we find the pattern, we define the result of the problem to be the continuation of the pattern. So 10 to the third, let's go down to 10 to the second. Well, that'd be 10 times 10, or 100. 10 to the first would just be 10. And we see what's happening here is every time we reduce this power by 1, our result here is divided by 10. So this brings us to one important result here, 10 to the 0. For 10 to the 0, we've reduced the power by 1. We have to divide this by 10. 10 divided by 10 is 1. And we've mentioned this before. Anything to the power of 0 is 1. Then as we keep going, 10 to the power of negative 1, we'll divide by 10 here again, that'd be 1/10. 10 to the negative 2 divided by 10 again, that'd be 1 over 100. And 10 to the negative 3 divided by 10 again would be 1 over 1,000. So 10 to the negative 3 is 1/1000th. And we do see a link between the negative powers and the positive powers. We see that 10 to the power of negative 3 is the reciprocal, or 1 divided by 10 to the power of positive 3. And that's how it works for all of our exponents, is those negative powers are just a reciprocal of the positive power. 10 to the power of negative 7 would be 1 over 10 to the power of 7. So why do we care? Well, the reason we care is because this allows us now to go back to that basic concept of place value that we talked about and really look at the number theory behind where place values come from. We have a decimal number system. And in that word decimal, the prefix deci means, just go deci, base 10. And what base 10 means is our place values are exponents with a base of 10. Now we know this first place is the ones place. Well, we just saw that 10 to the power of 0 is 1. This next place was the tens place, or 10 to the power of 1. Hundreds would be 10 to the power of 2. 1,000s, 10 to the third. And we can just keep going up, 10 to the fifth, 10 to the sixth, as we move to the left, counting up in our powers of 10. And we can continue to do so going to the right. We know this is the 1/10, or 10 to the negative 1. 1/100th, or 10 to the negative 2. 1/1000th, or 10 to the negative 3. 1/100th, or 10 to the negative 4. And we can keep counting going off to the right. So our place values are just powers of 10. And we like to abbreviate numbers, so we often have a number like this, 5,700,000. And we would often abbreviate that by simply saying 5.7 million. But we don't have to write out that full word million here. What we can do is we can just use the place value of that digit as a power of 10, right? Rather than the word million, we can just do 5.7 and then times 10 to the sixth. Most of you probably recognize this as our scientific notation. And this is really the heart of scientific notation. It is simply dealing with our place values. And what we're doing is kind of reducing really large or really small numbers down to their first digit and then a place value that that first digit is in. Here, the 5 was our first non-zero digit. So we put that there. The decimal goes after that to signify that that's the first digit. And then we name the place value, the 10 to the power of 6. The same would be true if we had 0.00083. So here, the first non-zero digit is the 8, so we're going to put the decimal point after it. So we call that 8.3, and then the 8 is in the 10 to the negative 4 place, so times 10 to the negative 4. And this is where, like I said, this is where scientific notation comes from. It's actually naming of that place value of what is referred to as the first significant digit. We're not going to get into significant digits in this class, but if you had chemistry or physics, you've probably talked a lot about significant digits. And that's digits that are part of or significant to a measurement. And in sciences, of course, everything is about measurement and precise measurements. But we don't really want to draw out the number line every time we convert numbers from standard notation or decimal notation into scientific notation. So we're going to look for a shortcut. And it's probably what you were actually taught was just the shortcut rather than this actual layout. So we look at the 5,700,000. The 5 is the first non-zero digit, and we're moving the decimal point to be after the 5. Well, there wasn't a decimal point in that number before, so it started at the end of the number. And so we had to move it to get it here to be after the 5. We had to move it 1, 2, 3, 4, 5, 6 places, hence the 10 to the 6th. Over here for the 0.00083, 8 was our first non-zero digit, so we had to get the decimal point after it. And it started here, so we had to move 1, 2, 3, 4 places. Well, how did we know that that was 10 to the negative 4 instead of 10 to the positive 4? Well, because this is a really small number. It's less than 1. Remember, 1 is 10 to the power of 0. So anything smaller than 1 has to have a place value of 10 to the power of a negative number. So this is in the place values that are negative powers of 10 because it's a small number. So we knew that had to be a negative 4. When you've learned this before, you're probably just taught memorizing negative is to the right, positive to the left, whatever. It's not necessary. You just know that negative power of 10 place values are the really small numbers that are less than 1. Positive power of 10 place values are the numbers that are larger than 1. So if I want to convert 0, 0, 0, 0, 0, 2, 6. Well, my first non-zero digit here is the 2, so my decimal point is going to have to go after that. So this is going to be 2.6 is what my start of my scientific notation is going to look like. Times 10 to the power of, well, I have to move my decimal point. Right now it's here, and I have to get it over to here. So I'm going to go 1, 2, 3, 4, 5, 6 spots. So my power of 10 is either 6 or negative 6. This number was small. It was smaller than 1, so that means its place value has to be in the negative powers of 10. So it's 10 to the negative 6 is the place value. Or if I had 490 million. Well, again, this is the first non-zero digit, so my decimal point is going to go after it. So I'm going to have 4.9. It'll be the start of my scientific notation. Times 10 to the what power? Well, the decimal point started over here, and I have to get it over to here. So 1, 2, 3, 4, 5, 6, 7, 8 places. So the power on 10 is either 8 or negative 8. This is a large number. It's bigger than 1. So we know it's a positive power of 10 place value. So that is 10 to the power of positive 8. Going the other direction, we just have to reverse the process. If I have 3.7 times 10 to the 7th. Well, I start out with the 3.7. And I have to move the decimal one direction or the other. Well, this is 10 to the positive 7. Since that's a positive power on my 10, this is a place value that's a large number. So I have to make this 3.7, I have to make it larger by moving the decimal point 7 places. So I move 1 spot, and then I'm out of digits, so I got to add zeros. So that's 2, 3, 4, 5, 6, and 7. So I come back, put in my commas, that's 37 million is that number. On the other side, the other type of example we could have would be 7.8 times 10 to the negative 5. So again, we start out with the 7.8, and I have to move my decimal point to either make it smaller or larger. The negative 5 tells me this is a small place value, so this number was small. So I have to move the decimal point 5 places to make this number smaller. So I'm going to the left. I go 1. I'm out of digits, so now I add zeros again. So 2, 3, 4, 5. My decimal point is going to go there. So I'm going to rewrite this as 0.000078. Put my extra 0 in front of the decimal point. Now, one thing I want to point out here, not something we'll be tested on in this class, but in this class, our numbers will be in this form. As things move more and more internationally, outside of the US, things are done slightly different. First of all, 37 million. Most countries do not use commas to separate like we do. They just use an extra, now I exaggerated it here, but this is just an extra half space at each of those spots. So as you're typing, there's actually a half space that you can put in that fits that in. It's about the same size as the comma, it's just not quite as excuse me, not quite as visible as the comma is. Why do they do that when the comma is way more visible? Well, the reason for that is they use the comma in a different way. This number here would be written like this. In many countries, they don't use decimal points. They use the comma for the decimal point. So when you see a number like this, that position of that comma doesn't make any sense if you're thinking in our traditional use of the comma in our numbers. Here it is meaning it's a decimal point, what we would think of as a decimal point. So that means this up here. Like I said, we're going to use our commas and decimal points normally, but I wanted you to be aware of that if you read any international articles or if you end up doing any work with people from other countries or whatever, be aware of that notation. So as I said, this stuff today, scientific notation, is really important if you're going to do any science classes building up into a medical program of some sort. Chemistry especially, because in chemistry you're dealing with atoms that are so small we have to deal with a lot of them. So you're dealing with what's called a mole. You do a whole mole of atoms rather than just a single atom, because one atom is just too small to work with. Or you're dealing with charges like an electron volt in the charge of the electron, masses of the parts of an atom and stuff like that. They're all going to be either really small numbers or on the other side really large numbers that we have to use scientific notation because we just can't express that many digits. Now, for our purposes, we're going to keep the powers of 10 a little bit smaller. You know, it's not like an electron volt where we're going to be dealing with 10 to the power of negative 26 or a mole where you got 10 to the power of 28 or anything like that. We're going to keep them smaller just to make it easier to work with. But the process would be the same with those more realistic, larger numbers. So to review, let's talk about adding and subtracting numbers before we get into our sign word or sign notation. When we add or subtract, the big thing was we must have the same name. And then from there, once we had the same name, we combine the counts. and then we keep the same name. So having the same name. For fractions, that meant having a common denominator. For decimals, it meant lining up the decimal points and lining up all the place values. For whole numbers, it meant lining up the place values. For scientific notation, remember the name is in a place value. If I have 4.8 times 10 to the 13th, the part of that would indicate a place value is the power of 10. So when I'm adding or subtracting numbers in scientific notation, I must have the same power of 10. That is the same name. Let's say I have 4.8 times 10 to the 13th plus 2.3 times 10 to the 13th. Now, a little side note here, you see the parentheses in here. We're used to seeing parentheses and thinking we have to do something there first. Because parentheses can be an enclosing symbol. But remember, we discussed an enclosing symbol is just one of the things that the parentheses can do. They also can indicate multiplication. And when we had negative numbers, they just isolated the negative numbers so we knew it was a negative number. They're doing something similar to that here. They're just isolating the number in scientific notation so we know that this is one complete number and not individual pieces. So we go ahead and add here. When we add now, we've got the same name, both are 10 to the 13th. So we're going to go ahead and combine the counts. 4.8 plus 2.3, 7.1. And then we keep the same name, times 10 to the 13th. Now as we move on to the next step, we might have 8.4 times 10 to the 8th plus 6.7 times 10 to the 8th. We still have the same name. They both have the same power of 10, 10 to the 8th. But now when we combine the counts, we got 8.4 plus 6.7 is 15.1. There's a little bit of a problem there, but we'll come back to that in just a second. And we keep the same name, times 10 to the 8th. So the problem we have here is that there are 2 digits now in front of the decimal point. We can only have 1 for proper scientific notation. So we have to move that decimal point over to make that 1.51. Now again, when you probably learn scientific notation, you're most likely taught to memorize, well, if the decimal point goes to the left, the power has to get bigger. If the decimal point goes to the right, power has to get smaller. It's actually simpler than that. All it is this number got smaller. It went from 15.1 to 1.51. So that number got smaller, the count got smaller, the name has to get larger. So 8 plus 1 is 9, so the name is now 10 to the 9th. Think of it very similar to measurement. If you're measuring something and it's 2 feet long, if I want to convert that to inches, inches are smaller, so it's going to take more of them. It's going to take 24 inches. The name got smaller, the count had to get larger. Same here, just the opposite. The count got smaller, the name had to get larger. Had to be a bigger power of 10 by 1. We might have 7.3 times 10 to the negative 16th plus 9.1 times 10 to the negative 16th. We combine our counts. 7.3 plus 9.1 is 16.4. And we keep the same name, 10 to the negative 16th. Well, once again, we have 2 digits in front of the decimal point, so I have to move that decimal over, making that 1.64. Now again, this got smaller. It went from 16.4 down to 1.64. So our power, or the name, has to get larger. Now you have to be careful with the negatives here. Negative 16 plus 1 is a negative 15. What if we don't have the same power of 10? What if we have 9.73 times 10 to the 15th plus 8.6 times 10 to the 14th. Don't have the same name here. Well, these are relatively close. 10 to the 15th, 10 to the 14th is just one number off. If they were a long ways apart, like 2 or 3, 2 would be, we'd still be able to combine them, but if they're 3 or 4 apart, the numbers are too different in size to really matter. Like I said, we're not going to talk about significant digits in order of magnitude in this class. But if those powers on the 10 are more than a couple of numbers apart, they're different orders of magnitude, so we really can't add those numbers anymore. But here, since it's 10 to the 15th and 10 to the 14th, they're only one apart, we can go ahead and convert them. We have to change them to be the same. Typically, we go to the larger power. So this one will stay 9.73 times 10 to the 15th. This one is going to become 10 to the 15th. Now, we got to reverse the process we did up here. The power got smaller, the power got larger, I should say, went from 14 to 15. The number has to get smaller to 0.86. So now we go ahead and add 9.73 plus 0.86 is 10.59 times 10 to the 15th. And actually, we have 2 digits in front of the decimal point, so we're going to have to move that one more to make it 1.059. Number got smaller, power gets larger, so 10 to the 16th. When we subtract, the process is pretty much the same. We can have 7.3 times 10 to the 12th minus 4.9 times 10 to the 12th. We have the same name. They're both 10 to the 12th. So we can go ahead and subtract. We combine the counts. 7.3 minus 4.9 is 2.4. And we keep that same name of 10 to the 12th. Of course, we can run into the reverse of what we did with addition. We can have 6.13 times 10 to the 19th minus 5.84 times 10 to the 19th. So again, we have the same power of 10, so they have the same name. We can go ahead and combine them. So we're going to subtract the count. 6.13 minus 5.84. And what is that? 0.29, I should say. Times, we keep the same name of 10 to the 19th. Now here we have the opposite problem we had up above. The only digits in front of the decimal point are zeros. We have to have one non-zero digit in front of the decimal point. So I move that over to make it 2.9. Now the number got larger. It went from 0.29 up to 2.9. If the number got larger, the power has to get smaller. So 19 minus 1 is 18. Be careful here if we're working with negative powers. If we have something like 4.27 times 10 to the negative 15th minus 3.91 times 10 to the negative 15th. Well, again, we have the same power of 10, so we have the same name. So we're ready to go ahead and combine. We subtract. 4.27 minus 3.91 is 0.36 times, we keep that same name of 10 to the negative 15th. Well, again, we need to move this over so that we have a non-zero digit in front of the decimal point. That becomes 3.6, excuse me. The number got larger, it went from 0.36 to 3.6, so the power gets smaller. Negative 15 minus 1 is a negative 16. So 3.6 times 10 to the negative 16. When we multiply or divide, remember we do not need the same name. And then we're just going to combine the counts. Remember, we always combine the counts in some way. But then we also, when we multiply or divide, we also combine the names. So what this comes down to is for our scientific notation, it means we do not have to have the same power of 10 to multiply or divide. We could have 2.4 times 10 to the 8th times 3.5 times 10 to the 15th. Here it does not matter that these are different powers of 10. When we're multiplying, we don't need the same name. So 2.4 times 3.5, what is that? 7.2, 8.4, I believe. I'm going to double check that. It's been one of those days with the weather. Come on. 8.4, okay. Times, then we also combine the names. 10 to the 8th times 10 to the 15th. Remember, when we multiply exponents with the same base, again, both of these have a base of 10. When we multiply exponents with the same base, we add the powers. So 8 plus 15 makes 23. 8.4 times 10 to the 23. Or we might have 1.7 times 10 to the 12th times 3.1 times 10 to the negative 7th. So again, we go ahead and multiply the counts. 1.7 times 3.1, I believe, is 5.27. Then we also combine the names. 10 to the 12th times 10 to the negative 7th. Well, we add powers. 12 plus negative 7, positive 12, negative 7, is just 5. So 5.27 times 10 to the 5th. I've been careful to keep those small so far. But let's look at something like 10 to the 6.8 times 10 to the negative 7th times 5.3 times 10 to the 19th. So we combine the counts. 6.8 times 5.3. Giving us 36.04 times, then we combine the names. 10 to the negative 7th and 10 to the 19th. We do negative 7 plus 19 is positive 12. But now, just like with addition, we have an extra digit in front of the decimal point. You've got to move that over, make this 3.604. Now again, the number got smaller, the power has to get larger. Number was smaller by 1 place value, the power gets larger by 1. So that's 10 to the power of 13. When we divide, we can have, let's see here. 5.76 times 10 to the 17th divided by 4.8 times 10 to the 11th. Again, we don't need the same name. We don't have to have the same power of 10 because we're dividing. We divide the counts. 5.76 divided by 4.8 is 1.2. Then we divide the names. 10 to the 17th divided by 10 to the 11th. Now remember, when we divide exponents, as long as they have the same base, again, both of these have a base of 10. When we divide those exponents, we subtract the powers. 17 minus 11 is 6, so that's 10 to the 6th. We might have 6.76 times 10 to the negative 8th divided by 1.3 times 10 to the 14th. So again, we combine the counts. 6.76 divided by 1.3 is 5.2. Names. We also combine the names. 10 to the negative 8 divided by 10 to the 14th. That's negative 8 minus 14, or negative 8 plus a negative 14. Makes that a negative 22. We might have 3.24 times 10 to the negative 9th divided by 7.2 times 10 to the negative 15th. So again, we combine the counts. 3.24 divided by 7.2, I'm going to say again, it's 0.45. And we also combine the names. 10 to the negative 9th divided by 10 to the negative 15th. So remember, that's negative 9 minus a negative 15. Negative 9 plus a positive 15, which is 6, so 10 to the 6th. So be very careful with the negative powers on the 10. Something we don't do a lot of in this course, but it's good to know, is powers. Like 2.1 times 10 to the 9th to the power of, well, let's just square it for now, power of 2. Just like we did with our variables, if we had 5x to the 7th, we had that to the power of 3, we did 5 to the power of 3 is 125, and then we did the exponent. Power of a power, we multiply. 7 times 3 is 21, so x to the 21. We do the same thing here. 2.1 squared is 4.41 times 10 to the 9th squared. Well, 9 times 2 is 18, so that's 10 to the 18th. We might have something like 3.1 times 10 to the negative 7th to the power of, let's go to the power of 5. So we have to do 3.1 to the power of 5. 286.29151 times 10 to the negative 7th to the power of 5 is 10 to the negative 35. Now, we have 3 digits in front of our decimal points. We have to move it over 2 spots to make that 2.863. We'll probably round it off there. We move this 2 spots now, so our power has to change by 2. So the count got smaller by 2 places. The power gets larger by 2. So times 10 to the power of negative 35 plus 2 is negative 33. And of course, we can do roots. We can have the square root of, let's see here, 5.76 times 10 to the 16th. Now remember, it's not written here, but this is really an index on that root of 2. You take the square root of the number. The square root of 5.76 is 2.4. And then for the power, remember this is asking 10 to what power squared would be 10 to the 16th. Well, since you multiply the powers, this would be 8 times 2 makes 16. So when we do a root, we're doing the reverse. We're dividing the powers. 16 divided by 2 is times 10 to the 8th. Or if it were a cubed root of 1.728 times 10 to the negative 12. Well, again, we do the cubed root of 1.728, comes out to be 1.2, times, now we divide our power by the index of 3. Negative 12 divided by 3 is negative 4. So that's 1.2 times 10 to the power of negative 4. We're not going to do this part in this class, but like I said, if you were to go on to chemistry or physics, lot of chemistry in any sort of our medical fields to prepare you for advanced biology and anatomy physiology. If you get into physical therapy and orthopedics, there's a lot of physics in there. So this type of calculation comes up a lot. For now, I'm going to have you work on homework out of the book. Page 84, problems 1 through 31. Just do the odds. So 1, 3, 5, 7. And then page 87, 88. 1 through 39. Also just do the odd numbered problems there. 1, 3, 5, 7. So with that, thank you for logging in today from home. I realize it's a little bit different. Hopefully the weather improves and we'll see you all in the classroom on Wednesday.